All right. So yeah, we're going to continue where we left off. This is probability with permutations and combinations. So we're going to look at permutations and combinations today, which is, yeah, you'll see this a lot in statistics. Um, so we saw the factorials last time. So factorials, remember, um, whenever you have a number and then you want to multiply it by the previous numbers, then that's the factorial. Okay, so 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. So all the numbers before 7, you're multiplying all those together. Okay, and you could use Desmos or use a calculator to calculate that. Okay, but the factorial is needed for permutations and combinations, so make sure that you know that. And we'll also see it on other problems as well. Okay, so the first one we're going to talk about is permutations. So the fundamental counting principle can also be used to determine the number of ways that n objects can be arranged in a certain order. Okay, so in this case, it has to be a certain order. An arrangement of n objects is called a permutation of the object. All right, so sometimes if the number of objects and the number of places or things to order it in are the same, then it's going to be the permutation of, um, it's going to be n objects permutation. So here, so n objects, permutations of n objects at n times, n at a time is going to be n factorial. All right. Now, the number of permutations of n objects taken at r at a time is going to be n factorial over n minus r factorial. And it looks difficult, but a lot of things cancel out. So yeah, we'll see both cases later. Let me put this on a note. All right, and there's an example if you want to see that. There's another one. And then we're also going to see combination. So combinations is where the order is not really important. Okay, when the order isn't important, usually it's going to be a smaller number. Okay, so here our answers are going to be a little bit smaller. So combination of n objects taken r at a time is calculated by dividing the number of permutations by the number of arrangements containing the same element and denoted by NCR. All right. So the number of combinations of n objects taken r at a time is n factorial over n minus r factorial times r factorial. And then, so again, the difference is order is needed for permutation. For combinations, it's not really needed. Okay. So combinations, order is not important. Permutations, it is important. Okay. So that's why we have EF, but also FE is okay. For combinations, EF is okay, so we don't need to write FE because it's the same. Okay. Permutations, we have GE, that's why and also EG is okay. But for combinations, just EG is fine. Okay. So again, order is not important. So let's put this in my notes. All right, there's an example. All right. So here, we're going to look at these. So let's look at permutations first. First one we have is where the n and the r are the same. So when the n and the r are the same, remember that means you just get n factorial. All right, so here in this case, it's going to be 6p6 is 6 factorial. And if you do 6 factorial, just go to the calculator, put 6 and then exclamation mark, we get 720. All right, and for 10, notice that the n and the r are different. So we have NPR, that's going to be n factorial over n minus r factorial. Notice how the n minus r is in parentheses. Okay, that's going to play a part here. So 5p3 is going to give us 5 factorial over 5 minus 3 factorial. And 5 minus 3 is going to give us 2. So we have 5 factorial over 2 factorial. And remember, factorials are going to be all the numbers after that number multiplied together. So 5, 4, 3, 2, and 1. And then 2 factorial is 2 times 1. And look at that. So here, these cancel out. 2 and 2, whatever you have on top. And on the bottom, those cancel out. And we're left with 5 times 4 times 3. Which gives us 60. Ta-da! All right. And then here, we have combinations now. Okay, for combinations, it's going to be and the r is n factorial over n minus r factorial times r factorial. That's the difference. So we have 7 C4 equals 7 factorial over 7 minus 4 factorial and times 4 factorial. So here, just like the permutations, this one cancels out. 7 times 6 times 5 times 4 times 3 times 2 times 1 all over. And 7 minus 4, I should have done that first. Oops. And now I had to write it all over again. All right, so you have, actually, so here, hopefully this is going to be okay. I'll just write it so you can see. We have 3 times 2 times 1. Then for that 4 factorial, we have 4 times 3 times 2 times 1 right down there. So that 4 factorial cancels out all of these, and we're left with 7 times 6 times 5 over 3 times 2 times 1. All right. Now, if you want to simplify, yeah, that'd be good. Okay, you don't need to do it right away, but yeah, 3 times 2 is going to give us 6. So there you go. These cancel out. And we're left with 7 times 5, which is 35. Ta-da! So let's do another one. Wait, when does class end? 25, okay. All right. And then you could try these out for the others. I think that's good. And then we'll go over a word problem because I do want to show you a word problem. So I'll put this up on the board, on the notes, so you could try those out. And if you have permutations, remember just n factorial over n minus r factorial. Combinations, n factorial over n minus r factorial times r factorial. Okay, but I do want to show you a word problem. So here at Grant Senior High School, there are 15 names on the ballot for junior class officers. There will be five will be selected to form a class committee. So there's going to be 5 officer positions available, but 15 people are trying to get into those 5 positions. Okay, so let's find the different combinations that we can do. So how many different committees can be formed? So does it say that the order matters? It doesn't matter. Okay, so in this case, it's going to be a combination. All right, so here we have 15 names. That's our N. And how many positions are available? 5. Okay. So openings and people. All right, so for A, we have 15. And we have 5 for R. So it's going to be n factorial over n minus r factorial times r factorial. Just plug in those n's and r's. So 15 factorial over 15 minus 5 times 5 factorial. All right. And 15 minus 5 is going to give us 10 factorial times 5 factorial. So I have 15 times 14 times 13 times 12 times 11 times 10 times. Okay, I don't want to write all that. I'm going to put 10 factorial. Okay, everything after 10 or before 10. All right, and there, this one cancels out with this. And it's always going to be the case where if the top is bigger than the bottom, then you're going to take out part of that. Okay, so whatever that bottom is, that's the part that we take out on the top. Okay, so there we have 15 times 14 times 13 times 11 times 12 times 11 divided by 5 factorial. If you put that on desmos.com/scientific, we end up with 3003 possibilities. 3003 different ways to arrange that. Those 5 offices with those 15 people. All right. Now, in how many ways can the committee be formed if each student has a different responsibility? So here, this one matters. Order matters. All right. So in that case, we have permutations 15 P5. And that gives us n factorial over n minus r factorial. And then we showed this already. We had 15 factorial over 15 minus 5 factorial. And there, just like before, we had 15 times 14 times 13 times 12 times 10, 11 times 10 factorial. Actually, let's move that down there below, because it looks like we're running out of space. And 15 minus 5 is 10. And then 10 factorial and 10 factorial, they cancel each other out. And we're left with 15 times 14 times 13 times 12 times 11 is 360,360. So that many. All right, and now C, this is going to be a little different. It says if there are 8 girls and 7 boys on the ballot, what is the probability that a committee of 2 boys and 3 girls is formed? Now here we want to use combinations for each different case. Okay, so these are going to be different. We have 7 boys or 8 girls. Okay, now for the boys we have 2 openings. For the girls, 3 openings. Okay, so here for the boys, 7 C 2. And there we get 7 minus 2. I don't think I can color coordinate it anymore. Take too long. All right, so I have 7 prime over 5 prime. Sorry, factorial times 2 factorial. So that's going to be 7 times 6 times 5 factorial. And there we get these cancel out. We're left with 7 times 6 times 2 factorial, which gives us 6 divided by 2 is going to give us 3. So 7 times 3 is going to give us 21. And now we're going to look at the girls. Girls, we have 8c3. So 8 factorial over 8 minus 3 times 3 factorial times 7 times 6 times 5 factorial over 5 factorial, 3 factorial. So the 5 factorials cancel out. And there you go. So 3 factorial is 6. 3 times 2 times 1 is 6. So 6 and the 3 factorial cancel out, and you're left with 8 times 7, which is 56. All right, so then, almost done. What we want to do is we want to multiply those two together times 8c3. It's going to give us 21 times 56. And we want to divide it by the total. Okay, so what's the total here? Total possibilities is going to be 3003. Let's do this. 15c5. So 21 times 56 is a number. Divided by 3003, it's going to give us a decimal. Oh, we know we're dividing because we want the probability. So we want to divide by how many possible possibilities there are. Okay. The chances of the boys and the girls divided by the number of possibilities, the total number of possibilities. And when you do that, you get decimal, you get 0.39. Okay. The book wants it in fraction form though. So 21 goes into 3003 perfectly, so it becomes 56 over. And Desmos has a nice button on the right side. It's like a square over a square to convert it to fraction form, and it'll become 56 over 143. Ta-da! There you go. Or 39% chance. Okay, I'm getting 2 boys and 3 girls. And that's it.